It feels like a shame that there's only one day left of Amazon Remars. And when we talk about new technology, there's this old saw that I think a lot of us love to trot out, that our phones have more computing power than the Apollo guidance computer that got Neil Armstrong to the moon. I would like to point out that Moore's law has continued linearly such that it's very likely that the chip in your charging cable now has more computing power than the Apollo guidance computer. Over the past few days, we have taken a look at the incredible real inventions, innovations, and products that are altering our day-to-day life. From AI to robots to spaceflight, it really wasn't that long ago that these were concepts only in our imagination, that could be brought to life only through things like television and books and movies, and now we have them in our cities, in our homes, and in our pockets. Today we're going to hear a bit about how, that work is made possible through AWS, the engineering work that takes state-of-the-art theory and science and puts that lightning in a bottle, making tools that allow builders to make their wildest ideas into a reality. We'll start with Swami Sivasubramanian, who will cover machine learning, working through everything from AI-powered productivity tools all the way down to looking at how we think about data structures. Then we'll hear from Ronnie Sohl and Bill Voss, showing us how simulation technology is pushing the envelope of the possible, from machine learning to robotics, and how robots are more capable than ever. I'm still holding out for my own personal BB-8. And what better way to finish than with the final frontier, space? Tom Soderstrom will show us how far we've come in exploring our vast universe and the technological shifts that are changing what will be possible for us all. So, without further ado, please give a warm welcome to Siva Subramanian, VP of Data at Amazon Web Services.
Hello, and welcome to second Remars conference. So today you will hear from myself and several other leaders in AWS talking about machine learning, robotics, and space domains at AWS. Remars is a special conference for me, where we come together as a team to showcase and discuss the technologies that are pushing the frontiers of technology and discussing the largest changes in our generation. By the end of today, I hope you will see that the experiences we have envisioned for tomorrow are much closer, and these technologies across these domains are more intersectional than you previously thought. Now let's start with the M in Mars, which stands for machine learning. Machine learning is one of the most transformative technologies we will encounter in our generation. It is already transforming every aspect of our daily lives and really revolutionizing every industry as well. And this revolution is possible because builders of all types are innovating in AWS. Not just the expert practitioners who are coding up the next big algorithms on the optimized infrastructures that we provide, but the machine learning model builders who are building these models and training and deploying them using state-of-the-art technologies like Amazon SageMaker, and then also developer services that we offer for incorporating AI into our applications as well. So today, what I wanted to do is show you three massive areas in machine learning that is pushing the machine learning space forward. The first one is all around natural language processing, or NLP. Specifically, I'm going to zoom into large language models, how it is pushing the tech space forward. Then the second area I'm going to discuss is around applying cutting-edge ML techniques, specifically with respect to data and around graphs. And then the third one is, how do you build these ML models quickly, but also highly accurate, using some of the latest technologies that are available? Let's dive right in. In the past few years, we have seen NLP space grow leaps and bounds with the ability to move beyond just simple sentiment analysis and entity detection to now these machine learning models can understand the entire documents. And large language models such as BERT and GPT-3 have really pushed the boundaries on what's possible. For instance, you can actually, with a simple prompt, generate entire text and synthesize them. So much innovation is happening in this space. And when you look at what does this all mean for us on a daily basis, beyond improvements on day-to-day life, it is changing the way work gets done. It is improving our productivity, allowing us to focus on our energy on what we love to do instead of what needs to be done. Let me give a few examples of how these NLP is actually in the hands of AWS customers today. NLP is unlocking the potential for data and users already. If you look at Amazon Kendra, which is our deep learning-powered search service, you can ask a very simple query in English, and it will automatically search all the documents and give you a highly accurate answer within the enterprise. If you look at the BI space, where you used to be gone are the days where you are actually connecting to a data warehouse and spend a couple of days, if not weeks, to find the right answer and build a dashboard. Now, using NLP and several other techniques, you can ask questions in simple English and get answers within a few seconds with an entire dashboard. The same thing we are trying to do now with Connect and Contact Lens, where you get near real-time access to customer sentiment and feedback and issues as well. So when we look at what are the other areas NLP can really push forward on what's possible and makes life better, one area that we seriously invested in is in the area of software development and operations. ML tools have fundamentally changed how software gets built and operated in the cloud. Now, if you look at what this does, typically software developers build these softwares, and then they test it, and then deploy, monitor, and so forth. This is where in AWS, we have offered technologies like CloudWatch anomaly detection and DevOps Guru, which actually ingests all these CloudWatch metrics and logs and ensures that it automatically looks for what patterns and is actually having an anomaly, and that helps developers identify these anomalies and remediate outages so that they can actually focus on what they really want to do, which is to author these application logic and build the next big thing. So let's dive into what does it take to build an application then. Now, as I said, developers have incredible power at their disposal today, thanks to cloud, machine learning, and several other technology. But when it comes to coding up from an idea I have to actually writing the application, there are a lot of hurdles one needs to go through. Ideally, I mean, they can reuse a piece of code that they have already written. But if that is not available, then they got to search a documentation or search the web and find which code is very relevant to what they need to build. And then they actually can start thinking about saying, like, hey, if they didn't find the code in which the programming language I'm already using, they find what they can and then tweak it to their language of choice as well. And so they may even have to adapt it altogether. So if you look at this problem in general, the result is that developers end up spending a lot of their time in doing what I call as the undifferentiated heavy lifting. And when I say undifferentiated heavy lifting, it's not the time spent in actually thinking about the business logic, about how to build the application. They have to think about syntax and semantics and all the various things related to how do I build it so that it is secure and how it is highly available and ensures it meets my operational criteria and best practices. So we asked ourselves, saying, like, so how can machine learning, specifically NLP, help here? So we looked at some of the ways that we can push the latest advancements in NLP and then address this problem on behalf of our customers. So that's why today I am really excited to announce the preview of Amazon Code Whisperer. It is an ML-powered code generation service that aims to help the developers more productive in authoring their code. Code Whisperer generates code recommendations based on contextual information, such as the code I have already previously written in my IDE, but also using simple natural language prompts, such as I can just write in the comments saying, like, generate a subroutine to upload files to S3. Then Code Whisperer automatically determines which cloud services I need to use and what are the best practices to use it for your specific languages. And it directly generates the entire subroutine in the IDE itself. Unlike traditional autocomplete tools, which work only one line at a time, Code Whisperer generates an entire subroutine. And the best part about Code Whisperer is that it lives directly in your IDE and supports major programming languages: Java, JavaScript, and Python. And it also supports IDEs, various IDEs such as VS Code, PyCharm, WebStorm, Lambda Console, IntelliJ, and Cloud9. Code Whisperer leverages the latest in large language models, and it is trained on a huge amount of data sets, including Amazon code and various open source code as well, along with extensive API documentation that is used to build all this knowledge base. And to make building applications on AWS easier and faster, we have trained the model on the most common patterns for building cloud applications as well, so that you can build and innovate on cloud much faster than ever before. So I know that Code Whisperer will boost developer productivity immensely, but it is equally important that we do this in a responsible manner. There is a lot of messy code out there and containing bias, security bugs, and secrets. So it is absolutely critical that we incorporate capabilities that mitigate these risks for developers. That's why Code Whisperer is highly differentiated, where it comes in with inbuilt security scanning. To help developers build applications responsibly, we provide security scans to detect vulnerabilities in developers' projects. And also, it has an inbuilt reference tracker feature, which detects whether a source code recommendation may be similar to the one on the particular training data, making it easier for developers to decide whether to use that code in their data projects or not. And finally, Code Whisperer also empowers you to avoid bias by removing code recommendations that may be considered biased and unfair as well. We see immense promise in applications powered by NLP, especially Code Whisperer, to help improve the productivity of software developers and help them write more consistent performant code quickly. Now, while we see innovation in what ML-powered features can achieve, we also see significant changes in the tooling landscape on how you process data and how you build ML models on top of them. Underlying all of these services, platforms, and tooling is the need to represent our data in a logical manner, in a way that allows us to process this easily. But historically, if you look at the machine learning techniques or even data store techniques, many of the streams of the information in our world have been analyzed in isolation from one another, one web page at a time, or one search query, one text passage, or one video. But in reality, the real world is very different and much more nuanced and complicated. We all know that these things are intrinsically connected. Let's take web pages for an example. A web page is linked to another web page through either a hyperlink or a sitemap. Or let's take a patient electronic health record, which has links to doctor's notes and then prescriptions, but also radiological images as well. Now, to push the boundaries of understanding all this data, not only to store, process, and query them, but also to run compute and machine learning on top of these, you need to represent this data on an interconnected data set. We have seen the emergence of graphs as a much more natural data structure for storing and traversing this type of data. And when I say graphs, I don't mean an XY axis with a line or points in it. A graph consists of two core concepts, nodes and edges. Nodes represent entities, which talks about, and edges are the lines between them, representing the relationships between the entities. There are fine-grained details such as key value properties of the nodes and directionality for these relations as well. Graphs are a very natural way when we think about examples like map of airports and the flight paths between them, or a social graph, where you can map the relationships of individuals and groups as well. So what can we do with these graphs? If we were to construct a data set of an airport in a graph model, you can easily answer queries like, find me a flight path from, let's say, Vegas to London Heathrow with no more than one layover. Now, as humans, we naturally reason about graphs because our mind works with interconnected data sets much more naturally. But for computers, it is not always that straightforward. First, you need technology to be amenable to actually be able to store, process, and query them at the data store level. And then you need machine learning algorithms to be able to process them, these graphs, at an efficient manner. And this is where Amazon already have been making a service available called Amazon Neptune, which we launched to help customers store, process, and query these large graphs easily. Now, thousands of customers today have been using Neptune to store their graph data for knowledge graphs, security graphs, and identity graphs, and more. And where graphs are representations of data, graph neural nets, or GNNs, allow us to apply machine learning to our graphs to gain even more valuable insights. I have deep conviction that GNNs are the next big thing, powering an emerging set of technologies like how Janssen is developing a novel protein folding solution with GNNs and large language models, or how COVID-19 drugs are being discovered with drug repurposing knowledge graphs as well. GNNs will alter the way you think about solving problems. We make extensive use of graphs in Amazon. They power our customer trust organization, a 30,000-person team leveraging tools built on graphs to identify marketplace abuse, such as fraudulent review schemes. Across Amazon, we have multiple $15 to $20 billion node graphs, and at our largest 100 billion nodes. And at AWS, the fraud and abuse team has a graph with 100 trillion edges performing class predictions for every node in the graph. With GNNs, this team was able to identify 10 times as many malicious accounts as the previous rule-based systems. They even power some of our AWS services today, such as Amazon Personalize for personalization and Amazon Fraud Detector for fraud detection as well. But how are graphs and GNNs different from traditional deep learning methods on normal data? Let's compare images and graphs. In images, concepts like orientation are important for pixels, but graphs do not have the same limitation, where a node's representation is the same even if neighbors are shuffled. Images also have a fixed size, allowing for efficient computation with dense tensors and numerical kernels, whereas graphs are sparse and irregular, with wildly different shapes, sizes, and a massive range of interconnectedness. This leads to computations with both sparse and dense matrices, which are super hard to optimize. So when you think about training and running training and inference on image data sets, which involve a large number of discrete objects, it's very easy to scale them out because they can be scaled in parallel as well. Whereas with graphs, you got to operate on a single giant graph that often requires machines to load the entire data set in memory as well. So given the unique properties of graph data structures and GNNs, comes the need for tools to be able to train them. Today, you can use Amazon Neptune ML, a capability for our purpose-built graph database offering, to make node, edge, or graph-level prediction tasks. Now, to further expand the access to GNNs, we have been contributing to DGL, the Deep Graph Library, an open source Python project with more than 10,000 stars on GitHub and over 200 contributors globally. Amazon started with graphs and GNNs way ahead of the curve, as it enables us to query complex data sets even at immense scale. We see graphs as allowing us to think with an extra dimension. If you're not using graphs to gain better insights with your data, I encourage you to try setting one up. If you're already using graph data, now is the time to train your first GNN. And AWS will continue to be at the forefront of ensuring this technology is effortless to use as possible. Now, having the right tooling for machine learning is equally important for GNNs as it is for every other part of the machine learning process. Practitioners are always looking for better ways to build, train, and deploy models, no matter the data type, business problem, or model architecture. Here, open source frameworks like PyTorch, TensorFlow, MXNet, and other tools have shaped the way the builders train and deploy ML models. And many of these frameworks are regularly used on Amazon SageMaker. Today, I wanted to take the time to talk to you about one of these frameworks, and that is AutoGluon. AutoGluon started as an internal project from two Amazonians with the humble goal of automating repetitive tasks that exist during ML experimentation. Today, AutoGluon is an open source Apache licensed project with over 1.9 million downloads that is purpose-built to streamline the ML journey for text, tabular, and numerical use cases. And it has contributors from Amazon, NVIDIA, Intel, Berkeley, and many more. And in a world where these training methods and models have pushed towards larger and larger models with more parameters, AutoGluon achieves these improvements by working smarter, not harder, using a combination of techniques like ensembling, stacking, and fusion. The result is the most accurate multi-model training and fine-tuning available today. AutoGluon takes on the burdens that are challenging even to great PhD engineers like feature engineering, model selection, and hyperparameter optimization, and automates traversing all these through during the experimentation phase. This functionality is commonly known as AutoML, which automates all the exploration of various options and configuration when it comes to ML training to help us arrive more quickly at an accurate model. With AutoGluon, developers can tap into all of this functionality to train their models with only 3 lines of code. Now, when you think about it, keeping up with machine learning frameworks is like a full-time job with so many new frameworks and models being created every single day. Today's state-of-the-art may be obsolete in the next few months altogether. So that's why AutoGluon is created with the mind at a higher level of abstraction, allowing you to automatically take advantage of all these ML frameworks, even as new ones become available via a single elegant API. Let's take a look at some of these techniques that make AutoGluon remarkable. With ensembling, we move away from trying to actually find the single best model and instead construct a blend of multiple models that contribute to single inference, resulting in a more accurate predictor. Then the second technique is AutoGluon performs multi-layer stacking, which is the most powerful ensembling technique. Commonly used by Kaggle grandmasters, what stack models do is it trains layer by layer rather than all at once with backpropagation like a traditional CNN does, allowing them to be rapidly trained on a regular hardware. And the last one is fusion, which helps create a model with inputs of various data types. With input fusion, AutoGluon can aggregate multiple models that fuse data types like images, text, and tabular data when making a single prediction. At Amazon, we navigate a broad set of questions about our product listing that we sell to our customers that usually result in a binary yes or no answers. Does a product need an outlet, or does it contain materials that may be banned in a certain country, or is it child safe? These are questions that are rather not explicitly enumerated sometimes. Now, this is where AutoGluon helps. Now, let's take, for example, this Gillette Fusion product listing. AutoGluon allows you to use all of this data at our disposal to answer a complex question, but what is intuitive, like how long does this product last, across mixed data types like product images, description, title, and many more. The model trained by AutoGluon can accept each of these fields as inputs and use them to surface a single answer to the problem. The best part is this works for any product for any type of problem. At Amazon, we have 20,000 different binary classification problems that are powered by models trained with AutoGluon, just like this. And neither the use case nor the flexibility comes at the cost of accuracy. So we tested AutoGluon against a number of live and historical challenges on Kaggle and MachineAg. And AutoGluon consistently scored a top 1% scores across sentiment classification, book price prediction, and Mercari price prediction, and many more as well. To me, the superpower of something like AutoGluon is not about accuracy. It is the incredible time to value. In one example, AutoGluon reached first place in less than 4 hours, and it took a team of data scientists over 2 months to beat its accuracy in the leaderboard score. Think of the opportunity value you get with the power of AutoGluon and AutoML at your disposal just with 3 lines of code. One company making use of AutoGluon is Capcom, a video game company that has created some of the most iconic characters and franchises since its inception in 1983. They use AutoGluon to do customer churn prediction and built a model with 94% accuracy. That resulted in significant cost savings for them. Now, AutoGluon is natively integrated in Amazon SageMaker, so I encourage you to try it out today. And with some of our newest features in version 0.5, like multimodal fusion and support for time series forecasting, we are excited to see the unique models AutoGluon is going to help our developers build. But in machine learning, tools are just one part in training more effective models. We have been seeing innovative techniques like transfer learning, simulator training environments, and synthetic data refinement, pushing the boundaries on what is possible with machine learning, as well as what industries it gets applied to. To tell us a bit more about these emerging trends and the role they play in the robotics space, please welcome to the stage Ronnie Soule, Software Development Manager at AWS.
Thank you, Swami. How do robots know how to deliver a package, flip a burger, or open a door? Some robots have tasks that can easily be defined by a common programming language. It's a mixture of inputs, outputs, conditions, loops, and logic. But the more autonomous a robot becomes, the more likely it's relying on some form of machine learning. One of the most significant advances in robotics in the last 5 years is the adoption of advanced perception systems that allow robots to see and understand the world in nuanced ways. These perception models are driven by machine learning applications, many of which are developed and running on AWS. Humans possess a remarkable ability to grasp and recognize objects in the dynamic environments of everyday life. For robots to assist us, we need to be able to emulate these abilities. Machine learning is the key to enabling this. Many machine learning breakthroughs are coming from research institutes like Columbia, MIT, and UCLA. We collaborate to solve real-world challenges using machine learning. And robotics is one industry where you see many of these innovations show up in applied forms, just like a robot delivering a package to your door. Here at Amazon, we also have a large and growing community of scientists who are actively researching and publishing innovative papers. Over 500 publications in 2021. Together, we're providing new ways and opportunities for students and researchers. Amazon is where research meets reality. We're not only envisioning the future, we're building it. We have over 200 facilities and fulfillment centers all over the world today, powered by robotics. We have more than 520,000 robotic drive units across 15 different types of robots in our fleet, which process over 70% of all customer orders. Let's take a closer look at our robotic fulfillment centers. You can see our robots move the pods to our human workers. It's a great example of how humans and robots collaborate, each playing to their strengths. In the video, we don't have people running up and down aisles. The robots do all the running. You can see those robots carefully designed to operate safely and avoid collisions. That's all controlled by systems at the edge and in the cloud. This robotic automation helps Amazon deliver packages more quickly and safely. This type of robotics brings together many disciplines, including computer vision, path planning, localization, and mapping. Many of our customers are using AWS machine learning to build robots in interesting ways. Boston Dynamic is a great example of that. Not only are they building robots that can walk around industrial settings, they can also use thermal sensors to detect defects and alert maintenance staff to issues before they turn into big problems. They can be trained to walk specific routes again and again, capturing analog readings, which computer vision systems built on top of machine learning can convert into digital insights, resulting in safer and more efficient site operations. Machine learning models learn best when provided with an abundance of sample images. Yet, it's often hard to find enough training data to capture the enormous variation and edge cases. And even if you get a hold of these real-world images representing all possible scenarios, the process of annotating them accurately can take months. It is, of course, possible to train a machine learning model with just a few hundred images. But if you need to build a robot, like Robin here, that is able to accurately recognize and pick up items, to do that, your machine learning model needs to be trained on many thousands of sample images. So what do you do if you just don't have the number of sample images you require? The answer is synthetic data. And that is why I'm excited to announce synthetic data generation for Amazon SageMaker Ground Truth. We're so excited about this. Synthetic data generation for Amazon SageMaker Ground Truth is a feature that enables data scientists to generate image data so they can train more accurate machine learning models. With synthetic data generation, customers can source high quality and accurate training data at scale in weeks. And this is at a lower cost than traditional data collection mechanisms, saving time and money. We're not only talking about the cost and time required to annotate images. These synthetic images wouldn't even exist in the first place. Let's use Amazon Box as an example. To start generating synthetic training images, you provide a 3D model of an object, perhaps a model of your product. Here, we've provided multiple 3D models of Amazon packaging in different shapes and sizes. If you don't have 3D images ready to work from, our team has highly specialized technical artists that can help you create them. You also supply a number of scenes that represent the environment that the object will be placed in. And then, Ground Truth will create as many images as you need of that object, generating synthetic images from 3D virtual environments that represent real-world scenarios, including physical forces and conditions such as gravity and lighting. You might think the photo on the screen is real, but in fact, it is a synthetic photorealistic image. Each photograph is created with your 3D model or asset, mimicking your environment and your camera configuration. This camera point is really important. If the robot you're building uses a 720p camera, you want the synthesized data to also be at that resolution. The end goal is to train an accurate machine learning models, so everything should match what your sensor will capture in production, from the camera resolution to the lighting. You configure the properties and variances that define each potential scenario, such as object pose, size, quantity, surface variations, and lighting. Next, you specify the number of images to generate as well as the desired label types, such as 2D bounding boxes, instant segmentation, and contours. Within hours, the service will generate thousands of diverse auto-label images and place them into your Amazon S3 bucket. And in case you find out that you need a few more thousand images, or if a new object type or variation becomes available, you can always kick off a new project and generate a new batch of synthetic images. Finally, you can use these generated images with other machine learning services on AWS, such as Amazon SageMaker, to train new computer vision models. Just yesterday, we heard here how synthetic data was used to build Amazon One. I can't wait to see how you will use this new feature. And there is so much more to robotics. I am so excited to share more about robotics and other ways in which the cloud is helping customers to build robots. Please welcome Bill Vass, Vice President Engineering at Amazon Web Services.
Thanks, Ronnie. It's really great to see how synthetic data can be used to improve machine learning models. We're going to ramp it up a bit and talk about synthetic worlds and how to do simulation. But the technology that Ronnie showed there can be used in a whole bunch of other industries outside of robotics. For example, improving satellite imagery or quality control in the food industry. But I'm really here to talk about robotics and the cloud and how they work together. During an average day, I think a lot about the cloud, and I also think a lot about robotics and how the cloud has transformed so many industries. I'm heavily involved here at Amazon in robotics, and when I talk about the cloud and robots together, a lot of times people kind of look puzzled to me as like, well, the cloud doesn't run on robots. I think people just look at the robot and see what the hardware looks like and those kinds of things, but they don't think about the software and the machine learning behind it that was developed in the cloud and gets pushed to the robot. And I think that's where it's really transforming things. Robots are thought of as independent entities, a collection of wires and servos and those kinds of things with some smart, clever software running on board, like R2-D2 or Johnny Five from the movies. And there's still a lot of edge processing, and we'll talk about how important that edge processing is for low latency and high performance on the robot as well. But the real power of robots is not the physical hardware. It's going to be the software and the machine learning that are used to train and orchestrate and manage them. And that's where the cloud is just transforming the robotics industry. For example, as we move to driverless vehicles, the hardware of a car really isn't changing that much, motors and engines and those kinds of things, wheels and tires. But it's really the software and the machine learning that enables autonomous driving. Historically, we've had this manual way to build robots, just trial and error. I remember putting my source code on a thumb drive and sticking it on the robot, and you'd manually test it in a lab, and it would bump into things, and you try it again, and you try it again. Really laborious process, and you were constrained to the physical environment of a lab. Took a long time to do that, but if you really want to accelerate robotics, you have to use simulation. As I often say, if your business is not leveraging simulation, you're basically standing still to your competition, right? Because simulation is changing everything. Like a lot of you out there today, I flew here on a plane with a well-trained pilot. And just as we're talking about using machine learning and a lot of data and simulation to train a robot, we've been doing it for a long time with things like pilots, and I even learned to drive initially on a driving simulator. Today, the simulations are quite advanced. In the past, not so much, but it's amazing now the kinds of things you can do in simulation. You can have extraordinary circumstances. You can have varied weather, even to the extreme. You can simulate failures, things that would be too dangerous to try in a real aircraft, and you can vary airports and terrain and those kinds of things. This also saves a lot of money because you don't have to have planes dedicated to it. Just like we see with machine learning, the more data and training you do, the better you get to be as a skilled human. Think about teaching a robot to drive. That's a huge problem. Ronnie explained earlier that these complex models require a lot of data. You need radar, camera, LiDARs, things like that, and you have to fill that data in and build a complex training model. You really need to drive millions of miles to do that. If you wanted to do that in the physical world, let's say do 1 million miles of training in the physical world, you need 2,500 cars traveling nonstop at 50 miles an hour for 8 hours a day. That's not very practical. But to really build a driverless car, you need tens of millions of miles that you need to drive every day. And that's physically impossible. And you just can't do it in the real world without simulation. Aurora is one of our customers that's building this new technology to allow cars and trucks to drive themselves. They're testing their vehicles in the real world all over the country as well. They use a combination of LiDAR and cameras and things like that and radar to see, hundreds of meters around them and 360 degrees. They run millions of simulations every day to accelerate this. Simulations allow them to test in virtual worlds at a scale and at a cost they could not do in the real world. They've built this amazing technology that allows them to simulate the way light moves through the physical world in these simulations. And they can vary roads and vary vehicles. They can have multiple intersections, changes in weather, change in lighting. And a lot of it is procedurally generated, and I think that's where things are going. When you're building software for robots, like we do in our fulfillment centers, simulation has a lot of advantages. So first of all, you're not constrained physically, right? You can have an infinite world, if you like, in the virtual world, and you're not constrained by hardware. You can simulate all sorts of scenarios that are really unusual and happen infrequently, so you can make sure the robot can adjust to it. You can run things in parallel and do years of training in just hours. So just like in the driverless car example, trying to do this in the physical world is not really effective. At Amazon, we've adopted simulation techniques to really speed up development. And a lot of the robots you've seen at this conference from Amazon are taking advantage of that simulation, where it's replacing manual tests. We're using simulation. It really becomes part of the training process. We're building high-fidelity models that bridge the gap between the real world and the simulation world. And robots can learn directly from these simulations. It allows you to analyze the data in real time, manage fleets of robots, and even deploy from the cloud to the robots. For example, when we started to put together our fulfillment centers, they were really built for humans, and a human would probably put things in alphabetical order like the Dewey Decimal System and those kinds of things. But through simulation, we learned that as you randomize the product much more, you can do a lot more in parallel rather than serial, and you can move a lot faster. So those kind of insights only come from simulation, and you can do this kind of testing before you build a fulfillment center. Okay, so we're all really excited about simulations. Now what? Building these virtual worlds like that to simulate your robot in. So how do we make it easy for anyone to build large-scale simulations? So to create a simulation, you'd have to hire a 3D artist, put the physics together. It gets to be expensive and time-consuming. However, with procedural generation, we can do it a lot faster at a lot lower cost. So we introduced RoboMaker WorldForge. It uses procedural algorithms to generate 3D environments. And you can see up here, those are all generated by WorldForge. They guarantee individual random houses, in this case. You can choose your surfaces, you can choose number of doors, number of windows, number of bathrooms, all those kinds of things. And it'll generate those for you. Of course, people are starting to leave their houses these days, so we're working on extending this to generate office buildings procedurally, fulfillment centers procedurally, and outside spaces as well. Once you have your virtual world, you can spawn out to hundreds of thousands of simulations if you want, and that's an actual robot there in a RoboMaker simulation. You might notice the resolution is lower than what Ronnie showed. That's because the resolution matches that of the robot. And you can do it without really understanding the cloud. Just click a button and spawn out these simulations. But in the real world, you're not just managing a single robot usually, you're having them work together for a common cause, and you need to orchestrate them. So that's why we developed and delivered IoT RoboRunner. So it allows you to have a bunch of pre-built libraries that developers can use for managing how the robots work spatially together, orchestrate them, and collaborate for a common task. Of course, you know, you've seen simulation here as a really powerful tool, but what if you want to simulate more complex, larger things? And this is where digital twins become important. So digital twins are a virtual representation of the physical object, right? Process or service. It mimics the object. You could have a digital twin of a jet engine, a car, a robot, a conveyor belt, a whole factory, a whole smart building, a whole city. In the past, when you wanted to do physical tests, you had to like change your production line manually and to try to optimize it. Now you can do that virtually, right? And this is a game changer in the long term. We're pretty excited about it, but you know, it's really hard to build these. You've got, you know, the 3D environment, how you can pull that together, you're connecting your IoT data, your cameras, all those kinds of things. So we released IoT Twin Maker, and it's a service that makes it easy for developers to build digital twins. So you can you know, build dashboards, you get your 3D environments, you can integrate your cameras, you can do buildings, industrial equipment, all sorts of things. It's going to really transform how digital twins are made from an ease of use perspective. However, you know, robots are operating well beyond the factory floor. They're doing the dull, dirty, and dangerous jobs out there. And they're out in the field performing tasks like search and rescue, in mountains, on ships, oceans, you know, working in wind farms and solar farms, those kinds of things, and even on other planets. And they need extra storage and compute as well. So we built a ruggedized device that brings AWS to them. It's called the AWS Snow Cone. This allows our robotics customers to connect it to their robots and do edge processing and storage, especially when there's no network. And they can ship the data back. You can run it pretty much anywhere, and because it weighs less than 5 pounds, it was specifically designed to fit on drones, on commercial drones, and I actually used one here to create a 3D model of my barn so that I could put solar panels on it in the best way. They're designed to handle extreme environments and run that compute and storage locally. And when I say rugged, I mean it. I asked my friend Adam, who was out here earlier, to see how just durable they were. So remember, please don't try this at home. Adam is what we call a professional.
In the 1970s, Tonka had an ad where they showed how durable their trucks were by having an elephant stand on one of their toys. And I remember being 9 and yelling at the television, "Give me a hammer and an hour!" Hey.
Put that out. Thank you.
I had to admit defeat, but that was fun.
I'm relieved that he had to admit defeat there, because robots operate in some pretty extreme conditions out there, and the snow cone and the snowball are perfect companions for robots. I hope today I've given you an idea of how we're helping people build robotic systems and autonomous systems from end to end. Our goal here is to provide a simple environment to develop, test, simulate, train, and deploy. And with this centralized control and decentralized execution with security every step of the way. We want you to be able to run your robot anywhere, anytime, with and without the network. For example, recently one of our collaborators, Axiom, in the space area, asked us to find a way to help astronauts manage on-orbit research and data more effectively. So we took the Snow products to a brand new, rugged, mobile edge location, space. So that's a picture on ISS, right? So today I'm pleased to announce and share that Axiom and AWS work together to fully integrate, certify, and operate an AWS snow cone on the International Space Station as part of the AX-1 mission. The snow cone, yeah, it's pretty cool, isn't it? So we were able to communicate to the snow cone, make changes to the code if needed, run machine learning applications right there on the edge in space, automatically generate tags for imaging, analyze onboard photos. And I think it really is going to accelerate things on the edge in space. This experiment successfully demonstrates how some of the storage, compute, machine learning capabilities are possible in low Earth orbit with existing AWS technology. And in the long term, we're committed to continuing to remove barriers for our space customers and enabling on-orbit needs in future missions. So watch this area carefully. And to tell you more about it and the future of space technology, I'd like to introduce my friend Tom Soderstrom to come up here and talk to you about it. Thanks, everyone.
Well, I'm excited. How cool is that? It's snowing in space. Thank you, Bill. It's great to be back at REMARS in person. And I must say, you are all doing your job. You're inspiring each other, you're being inspired by each other, and all of the intersections of machine learning, robotics, and automation in space. Before landing at AWS, I was Chief Technology and Innovation Officer at NASA's Jet Propulsion Laboratory, where I helped infuse new technologies into space missions and make engineers hopefully more productive. Now I serve as Director of Chief Technologies globally at AWS. So my head is now in the cloud, but I must admit, my heart is still in space. So it's fabulous to be here. I'd like to talk about three things, basically. How do we answer the age-old questions? I'll tell you what they are. And how do we take benefit from this new space economy, and what is it? And finally, how do we use all this data to help save our own planet? We as humans, we've been looking at the sky for millennia. 2,000 years ago, the data scientists of the time asked all these questions. Were they data scientists? Yes, they were. We just call them mathematicians and philosophers. And they published their findings in the great Library of Alexandria, and it took years for other people to start understanding it. And of course, Earth was the center of the universe. Well, imagine now that you're a scientist and engineer, which probably a lot of you are, and you're using a handheld telescope to help navigate the oceans. Then you turn it to the sky, and you realize that there are moons orbiting Jupiter. You can see the surface of the moon. And you realize that maybe Copernicus was right. Maybe Earth is actually not the center of the universe. Well, we've come a long way since Galileo. In this just last century, we walked on the moon. We explored Mars. We sent human objects, such as the one you're seeing behind me, Voyager, to the outer reaches of the solar system and beyond. We even discovered exoplanets. If we one day needed to export humanity, would we have a place to go? We discovered 5,000 of them so far, roughly, and roughly a fifth of them are in the habitable zone. So the difference now is that in the last 5 years, and for the next several years, it's no longer a spectator sport. Space is a participation sport. We have several people from NASA here, from Jet Propulsion Laboratory, and lots of builders and data scientists and citizen scientists, all talking and working together. And let's take a look at what enables this new space economy. A good example you heard about yesterday, which is the Orbital Reef Space Station. So it's the commercialization of space, where commercial companies and governments will work together. And you can think of this as a mixed-use business park, where it's for tourism, and that's a good thing, because it generates interest in space, but also as a place to do research that can only be done in microgravity. And if you want to be a tourist today, go into the exhibit space and take the virtual reality tour of this wonderful creation. So what are some other innovations that are enabling space? Well, you heard about machine learning. It's fundamental for any space mission, whether it's for analyzing imagery of satellites or planets, figuring out where to land, or if it's something as exciting as flying or driving on Mars. So this Perseverance rover that NASA and Jet Propulsion Laboratory created has to be able to drive itself, roughly 140 million miles away. No small feat. But what are we seeing now? We're seeing new generation. You heard a lot about machine learning from Swami, and we're just in the infant beginning. This having the snow cone in space, you can analyze the machine images, is going to be amazing. You don't have to go all the way back to Earth every time. Another enabler is autonomy. Autonomous system is a must for space. It takes an average of 2.5 seconds to get to the moon, 5 to 20 minutes to Mars, 20 hours to Voyager. These systems have to be able to perform autonomously. And they have to be able to be updated. Jet Propulsion Laboratory, for instance, even updates the satellites while they're flying or once they've landed on Mars. Amazing. Robots. Robots are enabling the space economy. They're helping us explore the foreign planets and make them safe for humans. And even something you can now fly on Mars with the Ingenuity helicopter, which is like flying a helicopter at 100,000 feet on Earth, which is pretty much impossible. So the impossible is becoming possible. We can think of these robots as things. So you have Internet of Things. You'll soon have Internet of Space things. And we saw from Lunar Outpost that you can now have a commercially built rover on the moon. It's an amazing future. So another driver here of the new space economy is dramatically increased interest in space. For instance, there are 23 new space agencies created in just the last 15 years. In addition, the barriers to entry have been decimated. Compared to 15 years ago, it's roughly 15 times less cost to build one spacecraft, 20 times less to launch it, and hundreds of times less to analyze it. So everybody can participate. It's much cheaper. So what are some examples of these innovations? Wildfires. I live in Southern California. I care a lot about wildfires. And if you can detect them earlier, you can save lives and structures. A company called Exi in Australia can use satellite imagery and detect wildfires within 3 minutes, alert the first responders that can then respond much more quickly. So what if you could actually move that up into the satellite itself? Now you can detect those wildfires in seconds if those satellites are communicating with each other. And you could have more innovators participate in building this if you had more internet access in the world, which projects like Project Kuiper is doing by launching satellites that will provide this access, so we will have even more builders participating. We're also fighting climate change using more these satellites. And we're looking for water. These are 2 NASA instruments that will be launched, one very shortly and one in a few years. And they are examples of these governments across the world working together to look for the key to life in space and on Earth is water, we think. So same thing on Earth. SWAT, for instance, is going to understand the chemistry of water and help with more fresh water and reduce floods and things like that. The other piece that's key here is it's generating a lot of data. These two alone is going to generate roughly 100 terabytes of data every day, and that's a lot of data. So space innovation is not limited to just space agencies and governments with huge resources anymore. AWS is helping to democratize the access to space. Let's look at some examples. Maxar. Maxar delivers high-resolution images and geospatial intelligence 24/7. They also predict major storms. To do that, they use high-powered supercomputers, except they no longer have to. They spin it up in AWS Cloud, and it finishes all those amazing calculations in 45 minutes, and then they're done. So instead of having a data center sitting powered up all the time, it's just 45 minutes of work, then done, and so that generates a lot of money that's left over for more research and science. So these are the type of examples of purpose-built, high-performance computing now democratized and available to everyone that's going to help. Also, you don't need to own even your own antennas anymore. You can use AWS Ground Station as a Service. It has 10 stations across the world. So if you missed one data dump on an orbit, takes about 90 minutes, you can do the next one and the next one. And you can now start controlling constellations of satellites. And when you talk about the machine learning and what you can do, as soon as the data hits the dish, it can be calculated on. So you can do real-time decisions. And you pay only for what you use. One example is Capella Space. So Capella Space has a constellation of satellites using the ground station, AWS Ground Station. And they're using synthetic aperture radar, so they can see through clouds, they can see at night. So first responders, or in a defense situation, they get their images, high-resolution images, within minutes. Highly unprecedented, amazing. So cloud and space go together very nicely. It's about getting the data into a place where people across the world can use it, and then getting the compute right next to it so you can calculate on it very, very quickly. So it means that US builders can reach for the stars without a big upfront investment and generate amazing results, an amazing amount of data. So if we look at data, we're creating a lot of data. IDC is estimating that we'll have 97 zettabytes of data created this year alone. That's 97 million petabytes. Much of it will be generated by users, but when you think about the Internet of Space things, it's going to be even more data. So what do we do with it? How can we benefit from this explosion of data? Well, we need to move it into what you're interested in. So if you're an oceanographer, or if you're interested in thermal or topographical, or want to save our coasts, we need to make it easy to use. So I'm really proud to work at AWS because one thing is the Amazon Sustainability Data Initiative that's taking advantage of making all this data accessible. So if you're a builder and you're creating data and you are creating data for the public good, you can store it in AWS for free. Storage is free, egress is free. We even give grants that you can convert this data so that other people can use it without being pure data scientists. Customers like NASA, NOAA, the UK Met Office is using this a lot. And the data sits along other data sets, including from customers like the Space Telescope Science Institute, the James Webb folks, and 100 petabytes of data across 337 high-value data sets. What can you do with that? Well, you can do a lot. For instance, National Center for Atmospheric Research and Silver Cooling in AWS are doing probably the most complex calculations there are, global climate change. There are millions of lines of code, thousands of computers crunching on petabytes of data to calculate and generate what does global climate change look like. This is now being made accessible to modelers and models across the world through the cloud. So we will see even better results on this, and saving our planets should be our key priority. So we're seeing builders accelerate the space economy with this massive amount of interest and lower barriers to entry, and it's customized into where they need to be. So in Zanzibar, looking at mangrove, and because it's a barrier to storms and rising seas, Digital Earth Africa is leveraging this. And this public-private partnerships is really driving this amount of innovation, and we're seeing it at this conference. Another one is the African Earth Observation Challenge. I was a mentor and a judge for them, and I was very proud to see all of the innovation that's happening. The winner was Astral Aerial Solutions, based in Kenya. They use drones to support farmers with actionable data, like health monitoring, precision spraying, and yield prediction. So making this data available is helping the local and the global economy. So we believe that having these innovation challenges is a great way forward. So I'm really pleased to announce that at REMARS, we launched the Amazon Sustainability Data Initiative Hackathon. It's a giant hackathon. You can use all of this data. You can enhance if you're a builder, enhance your reputation, enhance your resume, make some money, and help save the planet. You can sign up right outside here in the exhibition space at the ASDI booth. So accelerators, space accelerators, we did it last year. We got 160 entries, and we picked 10, and we gave them up to $100,000 worth of credits. And they did amazing work. These were startups. Together, they raised over $350 million. So space is a booming business. A couple of them, you heard from Lunar Outpost, Justin Cyrus yesterday, having a habitat on Moon and commercial rovers. EduBeast is another one. They take a different approach. They took satellite data and they put augmented reality on. So if there's a fire, first responders can see through the smoke and see where people live, even though if the signs are burned up. Satellite View is looking at, through thermal, from satellite images, to see if buildings are leaking energy or heat. That's a great way to start reducing the energy use, and for the building owners to not waste energy. It was so successful that we did it again. And this time you can see the winners, or the 10 that were selected. The difference from last year to this year, very much of an international gathering from all over the world. Last year it was mostly US, this year it's all over the world. And each of them will receive up to $100,000 worth of credits. So when you look at these names on the screen behind you, there are innovators behind them. They're builders just like you. So talk with them, meet with them, find your niche, and partner to help further drive the space economy. So let's take a look into the future for a second. Let's start with, you know what it is? James Webb Space Telescope. It is both sophisticated and hardy. It's a 21-foot telescope, 100 millions away in Lagrange point 2. It's powered by 132 actuators with nanometer accuracy to keep these 18 hexagonal mirrors aligned. And it's already survived a micrometeor strike. It's tough and it's sophisticated. It's so sensitive, it could detect the heat of a bumblebee on the moon. And it's going to help us look into the beginning of the Big Bang, about 400 million years ago, and after the Big Bang. And it's going to hopefully find new exoplanets, if we one day need to have a place to go. So how sophisticated is it? On the left is what Spitzer Space Telescope saw. On the right is the same image from James Webb Space Telescope, and it was still just configuring itself. In 2 weeks or so, we will see the first images from space by James Webb, and I can't wait to see it. So we've come a long ways since Galileo's space telescope, or his telescope, and to James Webb Space Telescope, seeing the moon to seeing into the beginning of the universe. So we're gone from publishing in books to, as soon as the data hits the dish, it's available everywhere across the world, so builders can help us move it forward. So I think we will answer these big questions that affect humanity very shortly. I'm also extremely inspired, and I hope you are too, by Artemis. We're returning humans to the moon, and it's going to launch its first uncrewed mission in just a few months. And it's going to have a permanent, at least the goal is to have a permanent moon base at the end of this decade. And then practice to go to Mars, and then have a Mars moon base. People are estimating maybe by 2050. That's an amazing future, and you can all make it happen. Your children or their children may walk on Mars. So as the universe is accelerating, so is innovation in space. Imagine being a space builder 400 years from now. Where do you think you'll work? What planet? What exoplanet? And what tools will you have at your disposal? And what questions will remain unanswered? So what questions can we answer in the next year, the next month, maybe even by just doing some moonshots that you're all doing together? I hear wonderful feedback that you're all really inspired by each other. So hopefully you're enjoying this conference, and hopefully you are in the exhibit space and seeing those amazing exhibits, and talk to each other. And please help us save this planet. Thank you very much.
I saved my favorite suit for last. Hello again. We hope that you are enjoying today's show. Day 3 of REMARS definitely doesn't disappoint, and the next 3 speakers won't either. Next up, you're going to hear from one of my heroes, Nicola Fox, who leads NASA's efforts to explore the star that makes life on Earth possible, our sun. Then Deep Utala from NVIDIA will show us how devices can be programmed using AI and deep learning to perceive and understand the world around us. And finally, Richard Browning, my friend, will wrap up the day for us with a demonstration of what it is like to defy the laws of gravity and make human flight possible. So let us not keep you waiting any longer. Let's welcome to the stage Nicola Fox, director of NASA's Heliophysics Science Division.
Our ability to make dramatic progress is often only limited by our ability to access the right technology and the right information. We find ourselves at a crossroads in science. On one hand, we operate in the same paradigm that has guided the field over the past decades, ruled by data, theory, and simulations. On the other hand, we're beginning to recognize that powerful new opportunities for scientific discovery are possible through our increased data volume and sophisticated methods to explore these data. The emergence of the hyper-connected digital society and massive quantities of data that it generates has led to new analysis capabilities that literally scale to the vastness of our solar system. NASA's mission is to expand human knowledge about the universe, the solar system, and the planet Earth. In this presentation, I want to tell you some of the ways that we are accelerating our scientific discovery by marrying the wealth of data and modeling techniques to the cutting-edge technology provided by Amazon Web Services. But first, I want to tell you about heliophysics. Heliophysics is basically the study of the sun. And why do we study the sun? Well, fundamentally, we are curious people. From the very first time that people looked up at that bright light in the sky and wondered what it was, we've studied the sun. Humankind has literally studied the sun for millennia. Ancient Babylonians recorded eclipses on stone tablets. Renaissance scientists peered through their telescopes, tracking sunspots. Eventually, we took to space, and the first satellites captured solar particles streaming past Earth. Each generation has always run against the limits of their tools. And so what do? We build new ones. And so today, that allows us to have a bounty of new research questions that we need to build yet more tools to answer. But the sun is also a star. But it's a star that we can go up and visit and study up close and personal. So what we learn about our star is directly transferable to other stars in other stellar systems in other galaxies. And that will help us as we continue our search for life elsewhere. But most importantly to us here on Earth, the sun can send billions of tons of solar material hurtling towards our planet at millions of miles an hour. We call those events solar storms, and they can be very, very destructive when they get here to Earth. Fortunately for us, our Earth is protected by a magnetic field, and that blocks all of the harmful radiation from the sun. It also protects our atmosphere from this stream of charged particles that is released by the sun's magnetic field. But the sun actually does more than that, more than just impact the Earth. If I take you over the poles of the sun now, so you're looking down, you can see a sort of spiral pattern of particles continually emanating from the sun. We call that stream the solar wind. And not only does the solar wind actually impact us here at Earth, but it in fact carves out a protective bubble for the whole solar system as we orbit through the Milky Way. So it essentially inflates a cavity that protects our solar system from the vagaries of interstellar space. Now, NASA's heliophysics division studies everything from the core of the sun to that tenuous boundary with interstellar space, and even actually beyond. But what I want to talk to you about today is what happens when an event, a big solar event, arrives at Earth. As I already noted, the planet's magnetic field is protecting us from the very worst impacts. You can see here how the magnetic field lines on the sunward side of our planet become interconnected with those of the solar wind. And that allows a lot of energy and plasma to enter into our magnetosphere, or our magnetic environment. In turn, our atmosphere can also get very superheated, particularly the oxygen ions there. And that actually causes the whole atmosphere to expand, and that can prove problems for spacecraft that suddenly find themselves in a different environment. Also, energetic electrons flow down those magnetic field lines, hit the gases in our atmosphere, causing them to glow and form the very beautiful aurora. Now, you know, space weather is important, and we talk about it a lot today, but even though I said that we've studied the sun for millennia, we actually didn't realize this kind of profound link between the sun and the Earth until 1859. And here you see Richard Carrington, a very famous astronomer who was looking through his brass telescopes and sketching sunspots as he did every day. And he noticed while he was looking at this particular sunspot group that there were sort of bright white flashes of light that appeared, and then they kind of disappeared. He knew something had happened, but didn't really know what it was going to do. Just hours after he saw this, compass needles at the Earth began to spin. The aurora was seen at much lower latitudes than they'd ever been recorded before. And in fact, the whole telegraph system in the US was taken down for a number of days, about 4 days. Now, that doesn't sound very important, particularly if I talk to kids and I say the telegraph system goes down for 4 days, and they go, And then I say, yes, but imagine if you lost the internet for 4 days, and panic will ensue in a classroom. So if we compare it with today, so I'm showing you data here from, this is actually from an event in 1989. The aurora overhead is like a current system in the sky, and that current system can interfere with our power grids. This one caused widespread power outages in the northern US and Canada. This is a very important event for us because it actually demonstrated how vulnerable our power grid can be. We know that there are much bigger events in our historical record. And as we sort of put more and more technology up, mega constellations now in space, a huge reliance on power grids, we really feel that reducing our vulnerability is a national priority. Now, these big events, fortunately, don't happen that often, but what I'm showing you here is one that happened in July of 2012. It was actually the most intense substorm event, or solar storm event, sorry, in the 150 years since the Carrington event. And you're probably wondering why you didn't hear about it. Well, the one thing that was lucky for us was it went off the side of the sun. But had this event happened 1 week earlier, it would have been on a direct collision course with us here at Earth. And the estimates are that it would have caused about $2 trillion of damage to the US alone. So we really want to take these things seriously, and we really want to know, how to study these. And so starting in the mid-1990s and onwards, we've really focused on taking the data that will allow us to make these sort of transformational improvements in our ability to predict when one of these events is going to come. So we have our spacecraft there looking at the sun all the way through the space environment and then into all the different layers of the Earth's atmosphere. And we know that within this huge volume of data, there has to lie the clues that will tell us which of these solar storms will in fact become one of these giant superstorm, very destructive events. But it's very hard for us to look at all of these different data and find these sort of often quite hidden signatures. And even though there are dozens of spacecraft collecting data, the data is still very sparse. Distances covered by a solar storm are vast. I mean, they're 93 million miles from the sun to the Earth. On top of that, disturbances that leave the sun can change during their transit to Earth. So, something that looks quite benign on the sun can then be very destructive when it reaches the Earth. So just like major storms that you're used to here on Earth, a solar storm is an interconnected set of processes. Both in space and on Earth, a developing storm can be intensified by background conditions or by merging of disturbances that don't normally encounter each other. Currently, NASA data archives house about 12 petabytes of space weather data, and this is increasing daily, and it's comprised of all kinds of different space weather observations, different instrument types, different things going from the sun all the way down to our upper atmosphere. And as I said, we know that captured in this data set is the web of processes that can produce a superstorm. But how do we detangle the information to find these signatures? So we were approached by AWS, Hannah Marlowe and her team, to partner on an AI ML project using our space weather data set. And so we thought, what a great opportunity to actually work on superstorms. But there was one huge complication when we were going to apply traditional machine learning techniques: the rarity of superstorms. So what we did, instead of doing sort of the supervised learning, was we focused on knowledge-aided machine learning, specifically anomaly detection. So we're looking for those signatures that really don't conform to the normal expected behavior of the space environment. Extreme events in space weather are particularly amenable to anomaly detection because fair to moderate space weather makes up the vast majority of our data sets. And so it kind of provides a perfect, quiet baseline on which to identify anomalies. And the other thing is, using AI and ML, we can use every single piece of data that we have on superstorms. It kind of relies on classifying superstorms based on anomalies instead of the usual magnetic indices and various other parameters that scientists use to categorize their storms. So the other issue, there are very few historical examples that can be used to train our algorithms. The vast majority of the observations actually take place much earlier. And so what we did is we used we leveraged for space science the investment that the industry has made in developing sophisticated anomaly detection algorithms, things that you would use to identify unusual patterns maybe associated with bank fraud or web server attacks. And that's what we used to investigate superstorms. It also allowed us to look at all of the data kind of simultaneously and pick up trends either happening at the same time or even time lagged as we looked at the different areas. So one thing that was a problem for us is finding something that we absolutely knew was a common signature of a superstorm. And that was one of the most spectacular phenomena that I've ever seen occurring in nature, and that is the Great Red Aurora. These things can extend to exceptionally low magnetic latitudes and cover up to 95% of the sky. During that Carrington event in 1859, blood red skies could be seen as far equatorward as Cuba and Jamaica. People could literally read by the light of the aurora, and fire trucks were actually sent out to find and fight what were thought to be forest fires. So now we needed to identify data sets which existed at the time of reported Great Red Auroras. Unfortunately, not many were available, as most of the storms associated with these predated our very sophisticated data system that we have now. So we had to turn to operational data sets that were not originally intended for science. And here we partnered with Colorado University in Boulder to work on sort of older operational data sets and kind of clean them up, remove the nuisance signals, remove the detector anomalies, and get a scientific product that we could actually use. So one thing that we found was we did know that in order to produce a large, great red aurora, we need to have an awful lot of very low energy electrons, and I mean a lot of them. And this is sort of counterintuitive because this is a really big event and we're looking for low energy signatures. If you had higher energy electrons, it would actually produce the more common green aurora, but we don't see green aurora, we just see red. So, you know, again, counterintuitive. The whole energy during a big superstorm actually drops. So it was hard to actually explain that. But we found that it does recover after the storm, and that maybe was a signature of a superstorm. So after working with literally years worth of data, we found another clue. And that is that the precipitation associated with energetic ions or positively charged particles was actually bifurcating, and it was coming much lower in latitude than the electrons. Normally you'd see them at the same latitude. We realized that these sort of soft ions were actually kicking what would normally be a sub-visual signature of the aurora. It was actually giving it the energy and kicking it into the visible range, hence spreading the aurora and making it cover that much bigger latitude. So now we have a couple of signatures that are in common. We have the drop in energy, we have the large population of low energy electrons, and we have this bifurcation of the two populations. Now we have signatures that are peculiar to superstorms. So this led us to the production of a storm scoreboard where the extreme scores indicate superstorms. You can see the more usual one there, which is with a sort of a more typical storm, and then those beautiful red aurora with the superstorm. So the next steps for us include adding sophisticated data sets from our Heliophysics System Observatory that aggregate the observational data from more than 50 spacecraft containing now images, time series, and telemetry data spanning from the solar corona all the way through the heliosphere to our Earth's upper atmosphere. And with the aid of our sophisticated machine learning technology, we will sort of continually pre-process and combine and develop visualizations that will drive future heliophysics research and innovation. So using this very simple signature that literally was previously hidden, we can now study what other signatures may exist that will allow us to identify, understand, and eventually predict these most devastating space weather events. And it's important that we do it now. We are in a new solar cycle. The sun has an 11-year solar cycle. You're looking at data there from the last solar cycle. You can see the contrast of solar minimum to solar maximum with the sun. December 2019 marked the beginning of solar cycle 25, our current solar cycle, and the sun's activity is already ramping up and will continue to do so until we get to solar maximum that is predicted for 2025. Now, in this new solar cycle, we are already seeing much higher levels of activity than were predicted based on the last solar cycle. It will, of course, impact our lives and our technology here on Earth, as well as our astronauts in space. But more importantly, this is the first solar cycle that many new commercial and government stakeholders will actually have to navigate in orbit. We've already seen a pretty big event that happened earlier this year. It was actually a fairly small storm, a fairly mediocre storm. It arrived, it mixed with background conditions and different processes, and it actually had a dramatic heating of the whole atmosphere. It lifted up our atmosphere and meant that the newly launched Starlink spacecraft were now in an area of very intense orbital drag, and they could not reach their operational altitude, and they re-entered. And so it is very important that we work on these events, we understand what is causing them, and then we can actually predict and mitigate the biggest events. And so I'll wrap up by saying, the more we understand what causes such space weather, and the more we can improve our ability to forecast and mitigate the effects. The power and speed of AWS with the analyses to predict our superstorms can be carried out by sifting through as many as over 1,000 data sets at a single time. The knowledge process is guided by our accumulated knowledge about superstorm features and by simulations to understand those interconnections. And since our anomaly detection algorithms improve automatically with experience, we know that there's so much more potential for discovery of new anomalous features that have significance to superstorms and even to everyday space weather. So with this unsupervised learning, we are likely to discover things that we just literally did not know before. And with this partnership between NASA and AWS, we are discovering the questions that we need to ask today to drive science and innovation of tomorrow. Thank you very much.
Please welcome the Vice President of Embedded and Edge Computing at NVIDIA, Deepu Talla.
Good morning. Impact of computer vision is increasing tremendously across all industries. Billions of cameras are either deployed or are being deployed in all sorts of spaces. You take a look at some of these industries, manufacturing, for optical inspection, defect inspection, worker safety, optimizing the flow of goods. Autonomous vehicles, so we have approximately 100 million cars and trucks come in every year. Almost 1.5 billion of these vehicles are on the road today, and most of them will have increased autonomy in the future. So computer vision is going to play a pivotal part. Medical imaging for MRIs, CT scans, and cancer detection. Retail stores for self-checkout, for inventory management and heat maps. Public spaces like stadiums for people safety and access control. Smart buildings, employee access control, parking management. Robots for navigation, robots for pick and place, and robots for human-machine collaboration. And then you have traffic, transportation hubs, and warehouses. All of these are increasingly using computer vision. The last decade has seen a great progress in computer vision with the advent of deep learning. In 2012, for the first time, we saw AlexNet was using deep learning and beat all conventional computer vision techniques, which were handcrafted features. And then in 2015, for the first time, ResNet achieved superhuman level accuracy for image classification. And in the last 5 years, we've seen more and more neural networks, amazing ones coming out for both object detection and classification, things like SSD, YOLO, and RCNNs. And recently, transformers are increasingly being used in computer vision, originally designed for speech. In 2018, we released StyleGAN for image modeling in open source, and that continues to be used quite a bit as well. And then one of the hottest topics in computer vision recently has been NeRF, Neural Radiance Field. Incidentally, the Computer Vision Pattern Recognition Conference is happening right now, and I believe there are over 50 research papers on NeRF. So NeRF essentially takes a few 2D photographs from various camera angles and poses and delivers a 3D representation, 3D scene representation. And we've, at NVIDIA, we've been working on this. We've released what's called Instant NeRF, which actually speeds this up by a factor of 1,000 times, effectively creating a 3D scene from 2D data in tens of milliseconds. So these are some of the great research works that in the last 10 years we've seen in computer vision. Even commercially, you've seen some amazing progress. Amazon Go, the amount of technology that has gone into it with the number of camera sensors in the stores, if any of you actually have the experience to try that out, a lot of image processing computer vision needs to be done. NVIDIA Drive, we've been working on autonomous vehicles for several years now, and level 2 plus functionality is going to come in Mercedes-Benz and Jaguar Land Rover vehicles with our software in 2024 and 2025. John Deere has been using computer vision for automating the tractors, if you will, for both without human operation, but also reducing the amount of herbicide that you spray for weeds by an order of a magnitude. And Siemens Healthcare has been using computer vision for oncology radiation. However, we still have a problem. I think we're still within the first inning or the first 10% of this journey. Computer vision deployments with AI is still really in research and big corporations. We still haven't figured out a way to make this democratized where every farm, every manufacturing plant, small, big, doesn't matter, can use computer vision. And so there's a reason why we are not yet seeing the broad deployment of computer vision. And that's for the lack of certain tools. So we've been working on these tools at NVIDIA and also working with Amazon on this. And there's 4 main things that I'd like to touch upon. First is, how do we create AI models efficiently? Second is simulation and digital twins. Third is building efficient runtime applications. And fourth is deploying these applications and managing these applications for the whole product life. Now let's double click into each of these blocks briefly. So AI model training. As you all know, AI deep learning requires data, lots of data. And in fact, human label data. Human label data and real world data is necessary, but still not sufficient. Recently, there's been a lot of progress made in the area of synthetic data generation. The advantages of synthetic data generation are obvious. First of all, the data comes auto-labeled, right? You can actually randomize the domains, for example, changing the backgrounds or the lighting, and it's super fast to do. So at NVIDIA, we've been building this platform called Omniverse, and one of the features of Omniverse is something called Omniverse Replicator that allows you to generate synthetic data very efficiently. So using a combination of real-world data and synthetic data, we can really speed up the data generation for AI models. Second, the AI model that you come up with is really going to depend on what your starting point is. I'll give you an example. Imagine you're an NBA basketball team, and you're trying to win the championship this year. You're one player short. Who are you going to select? You're going to probably select somebody who's a 5-10-year player to add versus adding a rookie. Well, unless, of course, you're Magic Johnson, that'll be okay. But otherwise, the starting point really matters, right? So what we're doing here is building high-quality pre-trained models for various applications in computer vision that you can use as a starting point instead of starting from 0. So start from something like a 70 or 80. And then the last one is taking that model and adapting it to your environment. It is very hard to take any computer vision model and expect it to work in all deployment scenarios. It's actually pretty much an impossibility. So which means you need to have some level of customization. So we've created a toolkit called TAO, stands for Train, Adapt, and Optimize, that you can use to fine-tune your model. So the combination of these 3 things, we have several hundreds, thousands of customers that are using these technologies to really speed up AI model creation by up to an order of a magnitude. Second, let's talk a little bit about simulation and digital twins. The case for simulation is very elementary. Well, it's simple. It's cheap, fast, and safe to do things in simulation. When I was just walking to come to the keynote stage, I saw a huge Fanuc robot arm. It's probably 500 pounds or 1,000 pounds with the TV stuck to it. Now, in the future, you want to have humans and robots collaborate with each other. Now, imagine this. That's a 500 or 1,000 pound of metal. Would you, as a human, be comfortable experimenting, operating beside it? I certainly would not be that one. So if we can move this to simulation, you can simulate it 1 million or 1 billion times. And then once you're sure, you can then bring it into the real world. Now, the challenge traditionally for simulation has been there's 3 things that you need to do to simulate something very well. Number 1, the accurate physical world modeling. So you need high-performance computing and physics processing. So we're able to do that on our GPUs. Second, visual fidelity of the simulation matters in many cases, not all cases. So ray tracing graphics. And third, artificial intelligence running both as hardware in the loop and software in the loop. So we've created NVIDIA Omniverse essentially is an authoring platform for creating digital twins. Number 3, now you created the model, you've simulated it. Now you need to run it on your target device, whether it's at the edge or in the cloud, doesn't matter. Well, it turns out, there's a lot of complexity in AI inference, given the number of models and the number of modalities that you need to support. So at NVIDIA, we've been working on this for well over 5 years, creating libraries and tools for accelerating runtime inference. We have tools such as TensorRT and Triton. And over 2 million developers from over 20,000 organizations have been using our AI runtime acceleration tools. Now, that's one part of the equation when you're talking about computer vision. A lot of people actually fall into this pitfall that running a computer vision is just about AI inference. No, it's not. You have to, of course, run AI inference fast, but then there's a lot of pre-processing and post-processing that you need to do. So you need efficient runtime frameworks, especially when you look at modern architectures, computing architectures that have CPUs and GPUs and accelerators and video encoders and image signal processors, and the number of things that you need to process simultaneously is mind-blowing. So we've created a tool for that called DeepStream for optimizing runtime computer vision applications, and over 300,000 downloads that we've seen just in the last 2 years. So combining all of our AI acceleration tools with runtime acceleration for the complete end-to-end CV application with DeepStream, we are making it easy for developers to deploy computer vision applications. And then number 4, deployment and management. If you think about deploying computer vision into a manufacturing facility or inside a robot, well, that robot is going to it's highly likely to be operating for the next decade, if not more than that. You definitely want to make it smarter over time. So it needs to be updated constantly, right? And it needs to be done in a secure manner. So you need all these software tools that are able to deploy and manage all these individual devices. And that takes a lot of frameworks. So there's several frameworks the companies that are working on. At NVIDIA, we have a tool called Fleet Command. AWS is working on similar tools. So there's a lot of tools that are necessary for us to deploy computer vision broadly. So those are the 4 fundamental pillars that are necessary in order to democratize computer vision. Let me touch upon how we are partnering with AWS and NVIDIA in this space. We've been partnered with AWS for several years now, started with providing our GPUs into high-performance computing and training. We also have our latest GPUs in the AWS cloud for both inference and graphics application. We've been working with AWS in the area of accelerating all the libraries for machine learning. In fact, SageMaker uses some of our TensorRT and Triton tools as well. A couple of years ago, we partnered with AWS in this area of edge AI and computer vision, and a product called AWS Panorama. So I want to share with you some of the success stories as to how AWS and we collectively, by solving those 4 things that I mentioned earlier, have been able to take computer vision from big deployments to taking it into smaller deployments. So 4 examples here. One is Phillips 66. It's basically a gas station. The problem is actually pretty simple. The problem that they're trying to solve is there are attendants, but there are multiple counters, and depending on the heat map, depending on the flow of traffic into that gas station, there's a line, the queue length is significant, they can ask one attendant to come in. Or the other one is with summer travel coming up, the restroom cleaning is actually, it's a simple use case, but sometimes you do it based on every hour, but sometimes depending on the foot traffic, you might have to do it in every 15 minutes. So providing simple insights with no data scientists required in any of that. You just plug in a device and it does all the management. Number 2, Tyson Chicken. They had a simple problem to solve. The problem was that I believe I'm a vegetarian, so I don't know exactly, but I think there's 8 pieces of chicken typically in that, most people that buy in those things. And they were trying to pack those efficiently, accurately into big pallets. Would you want a human to do that? Sit down and watch the number of things that are going in? That's such a boring job. So using AWS Panorama and using all the accelerated frameworks, the application was able to accurately count and basically make sure that every pallet was exactly the same number as it was intended. Cincinnati Airport, solving again simple problems. Before you go into the airport, one of the biggest problems we have is, at least I have, I'm driving up trying to pick up somebody. There are few people who are sitting there for like 1 or 2 minutes, right? And they argue with the security personnel there how long they have been in there. Now with computer vision, you can accurately decide, figure out exactly what it is, and there's no confusion there. And then even after security, all the airport operations have been automated using computer vision. And last, Port of Vancouver. Massive containers are shipped from the Port of Vancouver. Well, you can do computer vision, of course, in the port, but they have actually employed computer vision all the way when the container is on the truck way behind somewhere, and they're going to track it all the way as it enters the port. So these are just some of the examples. You can imagine that none of these will have their own data scientists to solve these problems. These are truly getting into the common areas. And basically that's the future of computer vision. So I think in the next 10 years, we're still in the first inning of this. We have a 10x growth more to go. And it's only going to happen if we make this simpler and simpler with all these different tools. With that, I'd like to thank you for your time and hope you all enjoy Vegas.
Please welcome the founder and chief test pilot at Gravity Industries, Richard Browning.
Flight. It's a subject that I think has fascinated me since I was a child. I remember many hours actually, as a kid with my late father trying to fly these very simple little model gliders. They're so basic compared to what you get with drones nowadays, but I remember, yes, lots of fun times trying to fly those and also rebuild them when having crashed them loads of times. Back in 2016, I hatched this seemingly ludicrous idea of, could you have a run at the whole challenge of flight, particularly human flight? Could you reimagine it in a way from a sort of ground up point of view, where rather than sitting inside a flight vehicle or being strapped to a flight vehicle, and we've done that very well, obviously, in the last 100 years, otherwise I wouldn't be standing here. What if you actually tried to employ the human mind and body in a much more kind of intimate way and kind of try and, as far as possible, standing here now, actually fly? It still sounds weird. I can't find a better way of describing it. And part of the inspiration was the time I spent with the British Royal Marines, I guess, learning myself to be able to push my body and my mind further. The military is very good at doing that. And I used to get into things like this, calisthenics, where you can learn to support your body weight in weird positions, highly impractical. That's not how we usually get on the London Underground. And it was an idea that I think evolved in my mind. And I got to the point where I realized the missing link, very simply, was horsepower. I'm not quite mad enough to think you can kind of flap your way to this outcome. So 2016, around March of that year, in a little country lane in the UK, and this is all alongside a day job. I was an oil trader for 16 years in the City of London. I didn't tell them what I was doing at the weekends. This was ground zero. This is getting a little micro gas turbine, baby version of what's on a jet fighter with a few design changes. Only weighs about 4 or 5 pounds and puts out about 40 pounds of thrust. And actually the big learning from that moment was that feeling was just this spongy force. It's almost just like leaning on that table. So kind of emboldened by that, there was an obvious step to take, which is now you have two, and now not a mop bucket with the fuel tank inside. Now I'm mobile. Now, if you watch this little clip here where I'm pushing, you can see now that's a lot of force. I mean, in kilos, it's 40 odd kilos of force, so you're getting close to 100 pounds of force. And it's really interesting to note, when you lean on it, actually that's easy. When you point it sideways, it starts to really kind of beat you around. Now, having had two work quite well, you can see the sort of natural progression of this journey. This was a great stage, because actually your arms are really quite you're in control of your arms, and that wasn't enough power to actually take off. So it was a nice stage to get to. This trial and error, with the emphasis on the error, process took place over the summer. We tried to work out where else you could attach thrust to the human body that would allow it to become as intuitive as a bicycle. It's amazing, how you just add a bicycle to a human body and use the mind for balance, and how intuitive and what a brilliant partnership that is. That was not such a good example, and the tether system really didn't work very well. However, the model that we started to kind of gravitate towards was one of an engine on each, or 2 engines on each arm, and the net thrust feeling like it was going up your arm, and then an engine on the back of each leg. But you see the problem in that clip. It's weird. As your leg starts to get lifted, your foot can't feel the ground anymore, and your brain starts to make your kind of legs pedal. It's a very weird thing. Anyway, I had to not only try and work out how to turn that off in my head, but also stop damaging the engines every time I fell over from a couple of feet on that farmyard. But by November that year, I suppose at the time, seemingly impossible actually happened, which was this very lame, fuzzy little flight, still fighting one leg. And that was it. That was actually turning mad idea into something that actually flew for 6 seconds across that farmyard. And it's quite fun to reflect at this moment, over the intervening 5 years since then, just how far we've come. And this is a sort of no attention span, 60 seconds run through that's already now out of date by quite some way, of the 200 events in 36 countries that we've flown. And they're either commercial events or otherwise military or search and rescue medical ones that you'll see soon. So it's quite nice just to see how far you can take a ludicrous idea, and I'll touch on this at the end. I'm a passionate believer in the process of innovation. It's one of take a seemingly crazy idea and then as safely and survivably as possible, fail your way to what you never imagined was possible. As long as, and the rule we follow, is if failure occurs, and it occurs all the time, or used to in the early days, I'm pleased to say it doesn't so much now, can you get back up again from a safety, reputation, and financial perspective? That's my, in the short time I've got with you today, that's my offer as a takeaway, and that's what I used to use actually running a trading book as well. It's all about being able to get back up from your failures, and it allows you to do crazy things like that. The fire has nothing to do with me, by the way. That is a bad timed slide when I'm talking about failure. Something I'm also very proud of with this ludicrous journey is that we haven't raised money since 2017 because we've actually sort of generated our own income from this in doing things like training over 500 people to learn to fly these. So there's a great location in the UK about an hour outside of Heathrow at the Goodwood Estate, if people know that. It's where the Festival of Speed in the UK takes place. It's all Spitfires and racing cars, and we fit in great. And there are louder things there than us. We're actually setting up a training center in just outside of San Francisco in Napa, hopefully this summer, and it's the most strange process. You're never going to believe me, but you get tethered up to this thing, you stand there, you feel the force on your arms, you realize you can lean on it, just like leaning on a table. It literally feels like that. The rear engine lifts you slightly forward, and then that magic moment that you see with a kid when you take your hand off the saddle and they just get it and they never think about it again, the same thing happens here. And the probably best example is one of these clients here you'll see is actually one of my 2 boys doing a great job in a second of applying the mindlessness you need to apply when you're learning to fly one of these. There he is, not got a clue what's going on. He's just smiling and enjoying the view. And if you think about it, that's what happens with riding a bike or surfing or skiing or snowboarding. This taps into your natural human ability to balance in a way that's frankly more, I suppose, intuitive than walking or running in some ways. In the same vein, in terms of how fast we're progressing, a massive catalyst to that I really feel I always try and shout out is additive manufacture, 3D printing. We're able to have an idea, get it CAD'd up, and then get that printed. Nowadays in polypropylene of all things, we've moved away from aluminium and titanium and steel just because it's frankly more appropriate, bizarrely enough. That can change in design within a sort of turnaround time of about 2 weeks. A couple of days to do the CAD work, a week or so to get the print back, and then we'll put it together, go for test fly it. So the ability for us to just iteratively progress is hugely enhanced by this wonderful technology of additive or 3D printing. Dancing around here, another example of why we're never done with this whole journey as well is, and you could do a whole talk on this as well, this is the journey of VTOL transition. So if you imagine a Harrier aircraft, or you imagine the F-35, they blow air downwards, you rise up, and then you start to transition into becoming an aircraft. We thought, well, we do the first bit, I wonder how close we could get to doing the second bit. Turns out, we could do the second bit pretty well. Now, we kept a bit of a lid on just how fast you go, because you've got around, with the latest suit, around 1,500 horsepower. There's about 350 pounds of thrust in that. So given the frontal area of a human, you're going to go really fast. So this little film here, which I don't like as much as the previous one, the last one was an amazing flight to actually experience. This is where we set the current Guinness World Record for how fast you've actually flown, or we've flown in one of these. I'll save the surprise for when you see the dial coming up in a minute. You get a nice example of how you gradually transition into flatter and flatter, and you have to use your body to actually maneuver rather than thrust vectoring. That is kilometers an hour before you think it's miles an hour. I'm not quite that mad. And this is a good example as well of how you transition back out. That's something that the Harrier and the F-35 people had to learn as well. We had to learn it in real time, which is quite exciting. You actually have to turn the power up because you've lost the aerodynamic lift. So another example of something, an amazing sort of foray we went down. However, in the limited time I have with you, I want to just touch on two areas, which I'll let play while I'm talking. And you might have possibly seen some of this online. It's gone around pretty far and wide. I was with the Royal Marines in the UK for about 6 years alongside my day job, and they put on this exercise. It was probably the, I don't know, culmination of 6 or 7 exercises, and the idea was, could you use the equipment for maritime boarding? So you've got bad guys on the ship. I know it's a Royal Navy ship, but run with me. How quickly could you get onto the bridge deck of the ship? And if you think about the alternatives, it's a pole with a caving ladder, and you have to try and snag the railings of the ship. It's a horrendous process. I'll let it play out at the end, and you'll see what they do now. Or you're a hovering helicopter with a fast rope and all the rest of it, neither of which you can use your hands, for people who think you can't use your hands. We have a helmet-steered suppressive weapon capability for those who are interested in that. This was 16 seconds to get to that bridge deck, and I could have just provided cover, but instead of that, I'm using the old technology and providing the ladder for those who don't have a jet suit. Strange amalgamation of the new and the old. But this has become a huge area for us. We are working now with about 7 different special forces around the world on the Allied front, and the more theaters and environments we end up getting to play in, the more we keep changing the rules, because you really can just move human resources up and move in a couple of miles within seconds and do a task and come back again. So there you go. You can see that process. I mean, personally, flying is a hell of a lot easier than doing that, especially at night in heavy sea. And there is the demonstration of exfiltrating back out, although I'm weirdly landing on the same ship I've just attacked. But anyway, ignore that detail. Now, the other big area that I'm really proud of, just bearing in mind where this started from in a farmyard alongside the day job, is the whole search and rescue, or let's say medical response role. If you imagine a paramedic on a motorbike, they cut through the traffic and they get to the casualty and they sort out breathing or blood flow or something else critical that's potentially going to end your life within the first, critical 40 minutes, 60 minutes. This is a mountain in the UK in the Lake District. It takes about an hour and 20 minutes to walk up at pace. The weather, you'll see in a minute, was really bad, and it tends to be really bad in this place, so you can't often get helicopters onto the top, so the only option is that walk. And if you've got a cardiac patient, they tend to, frankly, not make it. So we parked up. This is obviously a planned exercise, didn't just turn up. We parked up and left the vehicle roughly where the search and rescue guys or the mountain rescue guys would usually depart from, and managed to get to the summit in, I think it was 3.5 minutes. That was 1.2 miles that way and 2,000 feet in vertical ascent. It was quite a demonstration because, and I'll let it just play into the foggy part. It was quite exciting to actually be flying along with probably visibility down to barely from me to that screen. And I ended up just flying, looking at frankly, it was an iPhone app, map system where I could actually just follow waypoints. It got so bad that the 2 drone systems dropped out. I should be able to, it's a shame I can't fast forward this one, but there you go, you get an idea of the fog. And we got to the top, as I say, in about 3.5 minutes. That is something we're trying to roll out. We've got a paramedic already trained in the UK, and they should be operational by later this year. That's our hope. And it's quite nice because it's quite closely allied to the military role, but it's just tends to be, when you get there, you're being more friendly than the military folks. But in terms of working in bad weather and in difficult conditions, it's a great analogy. There you go. You can see an example of the weather. Now, I'm going to shuffle that on. I want to just take the opportunity to reflect on what I said right at the beginning, which is this subject I'm very passionate about innovation, because a lot of words are used around innovation, and I'm not always sure they're from people who actually are walking that walk. I'm passionate that you have an idea, even if it's a crazy one, even a childlike thought that seems impossible. There is a process you can go in where you work out as quickly as possible you can go and test that idea. This is what we do all the time. And go and take the risk of it failing. The critical thing is, and I used to do this running a trading book, and now I do it running Gravity, is if failure occurs, because it will happen all the time if it's a meaningful test, can you get back up again? Obviously from a safety point of view, but also reputationally and financially. And that is our magic sauce that we use to keep pushing this whole crazy journey ever forward. And somebody who knows a lot about that and is, I suppose, a gleeful embracer of things going wrong is your host, my good friend, Adam Savage, who I think is going to appear, hopefully, if we've coordinated this well. There he is. But thank you.
Can I just start by telling the story of how we met?
Go for it.
I got to tell you, so I'm at the TED conference. I'm wandering around in the haze that you wander around in the TED conference. And this Brit comes over and says, "Mate, you're a legend. I love Mythbusters. And I've just gotten here with my rocket pack." And I'm like, wait, the rocket pack I saw on YouTube last week?
This was the very first flight, other than the accidental raise in a parking lot in San Francisco. Let's ignore that one. The very first public flight. So it was pretty scary in 2017.
And I had seen the video like a week before. So I knew it was all really fresh. And you said, "Well, I haven't brought anyone with me. Would you be my ground crew?" And I was like, I've waited my whole life to be asked this question. Of course I'll be your ground crew.
It was brilliant. We'd never met before, and he literally dropped everything he was doing at that point and then just followed me to the behind-the-scenes room and helped greatly with the huge stress. I mean, it's bad enough doing a TED Talk for the first time anyway, let alone 10 minutes later to go and fall over in front of the world's media, potentially, with this creation. So you were a massive help.
I was wearing this exact jacket?
Yeah, you feature in the film. It's not mentioned. You're just standing in front of me helping it out, yeah.
I love that you talk so much about failing your way to success. And, you know, what we mean by failure is iteration. It is all just iterative, you know, burning through options. I'm curious if you have more of the failures on tape, because those are my favorites.
So it just so happens, yes, for special audiences, and I would be a fraud if we hid these, we can roll a few of those learning opportunities. Let's call them learning opportunities.
Absolutely.
Right now. So here we go. So many of them are very old, I'm pleased to say. That was running out of fuel. That one was actually the first Guinness World Record attempt we tried. This is fun. I just ended up trying to land whilst forgetting I had about 20 mile an hour forward speed, and I can't run at 20 miles an hour. There's nothing wrong with the gear here. You just let go of the throttle trigger. That was a compressor stall, which is an unusual one. I'm hovering away in the background. This is where we really rinse the engines way harder, and at sea level, where the air density is greater. We rinse the engines way harder than we should have done. We dropped 2 suits in the water at that air show. But you can see a good example of how we do float. A lot of people online say, "Oh, if you're going to die, you're going to die if you go in the water." It's like, if we hadn't thought of that, we shouldn't be doing this.
I love how much this feels like that whole sequence in the original Iron Man film, where
the
things just keep not working.
Well, the garage stage. Yeah. Yes, exactly. Yes. I mean, yes. We didn't smash. I don't have a lineup of quite those cars to smash into, but yes. This is my main aeronautical engineer, Alex. I think you've met Alex. He piled into the water, and you've definitely met Sam, my CAD designer, who goes in head first here. That was actually the same flight, and this is one of my stuntmen team who didn't quite jump late enough by the time he got the power in. If you're going to do a superhero launch, you've got to dial the power in first. But anyway, that was a learning opportunity. So yeah, there you go. There is some of our, all very low, all very sustainable, if you like. You just graze your knee at worst. And
the thing that I love about showing the failures and being really honest about them is something we learned on Mythbusters from the fans, is that it feels like a hug.
Yeah.
Right? It's easy to be awed by something like this and think, that is impossible. How did someone brilliantly come up with that? And they didn't. You didn't. You have slowly made it better and better and better over time.
Just showing that as the end result is 5% of the journey. And I often get fed up with this when you read like business books about just give everything, never give up, never say die. No, that's rubbish. Constantly learn and pivot and feedback. If you've got somebody lucky enough who never made any mistakes and got to become some billionaire, well, I'd like to meet them.
Yeah.
And if you just read a book that says that's how they did it, you really need to read the book about all the things that didn't work.
Yeah.
Because that's the process that will screw you over if you get it wrong. You've got to keep recovering from endless failures.
The last thing I want to say is when you finally got me to fly, you finally taught me how to fly, and I brought my arms in, and it's not about strength, it's about feeling it in your body. And I rose off the ground. It really did feel like every dream I have ever had about flying.
It is a, I mean, I'm biased obviously, but everybody that gets in this suit, there is a strange process where you do feel like that dream we sometimes have of walking, running, and you step and you just go wherever you want to. It is kind of like that. It's a lot louder, but it is like that, yeah.
Another big round of applause for Richard Browning. Richard, thank you so much, man.
Yeah.
What a pleasure.
Thank you.
I hope you enjoyed the final keynote here at Amazon Remars, and there is still more to see. We've got more sessions throughout the day, and you are not going to want to miss the party tonight. Shuttles start at 7:15 p.m. It'll have live music, entertainment, and my personal favorite, a BattleBots challenge. Yeah, you're going to get to see some burning, twisting metal before the end of the day. I hope to see you guys there. Thank you guys so much. It has been my honor to host this with you guys. Thanks for letting me wear my beautiful costumes, and thanks to all the incredible speakers. You guys have a wonderful day.